A 40,000-ton ship, anchored in calm waters, suddenly broke in two, without a storm, collision, or warning. The Crimson Polaris wasn't supposed to fail. Yet overnight, a cargo of wood chips became an international engineering disaster. How could modern design miss the silent forces that split a giant vessel at rest? The unexamined risks behind safe anchorage are about to be revealed. Crimson Polaris measured 656 feet from bow to stern, with a beam stretching 106 feet across, dimensions that placed it firmly among the giants of the bulk carrier world. Registered under the Panamanian flag, the vessel was purpose-built for a single, demanding task: hauling vast quantities of wood chips across oceans. On this voyage, its holds brimmed with 44,000 tons of wood chips, loaded in Thailand and bound for the port of Hachinohe in northern Japan. Unlike tankers or container ships, wood chip carriers are designed with broad beams and deep cargo holds to maximize volume, not just weight. This design allows them to carry lightweight, bulky cargo efficiently, but it also means the ship's structure must withstand unique stresses, especially when fully loaded. Every inch of the hull, from the reinforced deck plates to the transverse bulkheads, was engineered to balance the shifting weight of cargo and the relentless pressure of the sea. A crew of 21 managed the ship's operations, a team drawn from across Asia, with officers and engineers from China and the Philippines. Their responsibilities ranged from navigation and engine maintenance to monitoring the condition of the cargo itself. Each role was essential, especially on a vessel where the stability and safety of the load directly affected the ship's performance. At anchor, Crimson Polaris appeared steady and secure, a floating industrial complex waiting its turn to discharge in port. Yet beneath the surface, the combination of immense size, specialized cargo, and the realities of life at sea set the stage for forces that would soon test the vessel's limits. Regulatory oversight in global shipping is divided among several authorities, each with its own priorities and constraints. For a vessel like Crimson Polaris, inspection responsibility was shared between the flag state of Panama, the ship's classification society, and the port states visited along its trade routes. Regulatory focus and competing priorities shaped who looked and when. Panama, operating as a flag of convenience, registers thousands of ships worldwide. Its inspection regime, while compliant on paper, often relies on periodic surveys and documentation submitted by owners and managers, rather than direct, frequent physical checks. Annual and intermediate surveys are standard, but real scrutiny varies by registry and can be influenced by economic pressures to keep vessels in service. Convenience in registration can reduce the frequency of hands-on inspection. Classification societies set technical standards for hull strength, machinery, and safety equipment. These organizations conduct formal inspections at scheduled intervals, typically every year, with more comprehensive reviews every 5 years. However, these surveys can miss subtle signs of fatigue or corrosion, especially in areas hidden beneath cargo or coatings. The Crimson Polaris, built in 2008, had reached an age where material fatigue and microcracking could develop unnoticed between inspections. Bulk carriers are particularly vulnerable to stress concentrations around cargo holds and along the hull girder, where repeated loading and unloading cycles gradually weaken the steel. Fatigue and hidden corrosion are silent processes. Operational realities further complicate oversight. Maintenance budgets, tight port schedules, and the logistical challenge of inspecting large, complex structures at sea mean that some vulnerabilities remain latent. Even with no formal deficiencies recorded in public databases, the absence of documented problems does not guarantee structural health. The regulatory framework, shaped by international conventions and economic incentives, can leave room for hidden risks to accumulate, setting the stage for failure when conditions align. At 7:50 in the morning on August 11th, a distress call reached the Japan Coast Guard. The Crimson Polaris, anchored several miles off Hachinohe, was experiencing steering problems as strong winds swept across the bay. The bridge crew, faced with failing control, struggled to keep the vessel's heading steady. With the anchor deployed, the ship began to drift, the wind and current overpowering the holding ground beneath. As the vessel dragged anchor, the crew monitored instruments and attempted corrective maneuvers, but the response was sluggish. The hull, fully loaded with wood chips, carried enormous inertia. Within minutes, the Crimson Polaris crossed the shallow contours marked on their charts. The bow touched ground roughly 2.5 miles offshore. The impact was not violent, but unmistakable. A shudder through the steel, a sudden resistance that confirmed the worst. Initial checks on the bridge showed no immediate injuries among the 21 crew. Attention shifted to the integrity of the hull. Seawater began to seep into the forward holds, and the first signs of flooding appeared near cargo hold 6. The grounding had breached the hull below the waterline, allowing both water and some cargo to escape. The vessel's stability became uncertain. The crew reported their position and condition to authorities, initiating a response that would continue through the night. From this point, routine operations gave way to emergency procedures. Loss of steering and the grounding itself set in motion a chain of events that would push the Crimson Polaris far beyond its engineered limits. As dawn broke on August 12th, the Crimson Polaris sat in two pieces, its bow and stern separated by a jagged fracture just forward of the deckhouse. Oil began leaking from ruptured tanks almost immediately, forming a slick that stretched nearly 24 kilometers along the surface and widened to 800 meters at its broadest. The cold, gray waters off Hachinohe carried the heavy fuel oil toward the coastline, leaving a visible sheen that trailed behind the drifting wreck. With the ship split, both sections posed their own hazards. The bow remained tethered by its anchor, still afloat but unstable, while the stern settled on the seabed, its engine room and tanks exposed to the sea. Response agencies from the Japan Coast Guard and the Maritime Disaster Prevention Center mobilized patrol boats and recovery teams, but the scale of the spill quickly complicated containment. Oil booms and skimmers proved difficult to deploy around the unstable wreckage, especially with shifting winds and currents. Adsorption mats and dispersants were brought in for shoreline cleanup, yet the sheer length of the slick outpaced early efforts. NYK, the vessel's charterer, dispatched more than 100 personnel to assist, coordinating with local authorities as oil and wood chips began washing ashore. The cold coastal waters presented another challenge. Heavy oil thickened in lower temperatures, making recovery slower and less efficient. As the slick spread, responders faced the dual task of protecting sensitive marine areas and preventing further leakage from the stranded hull sections. The twin-section wreck, still holding much of its remaining fuel, became both a logistical puzzle and an ongoing environmental risk. Each hour, the window for effective containment narrowed, highlighting the complexity of managing pollution from a fractured ship at sea. Hull girder theory treats a ship as a single, giant beam, one that must resist bending as it rides over waves or grounds unevenly. When Crimson Polaris grounded, the midship region bore the brunt of new forces. Flooding in the center holds increased the weight pressing down amidships, while the bow and stern, still supported by water or seabed, acted as opposing levers. This created a sagging moment that pushed the steel beyond its design limits. Under these conditions, even minor fatigue cracks or weakened welds, often invisible during routine inspections, can grow rapidly. Each passing wave flexed the hull, cycling stress through the same points again and again. Over hours, microscopic cracks lengthened, linking together until the steel could no longer hold. The fracture between holds 5 and 6 was not a single break, but the endpoint of thousands of repeated stress cycles acting on vulnerable metal. Shipping regulators and industry leaders began reviewing hull strength criteria in the aftermath of the Crimson Polaris incident. Investigators noted that while bulk carriers are subject to routine inspections, the lack of real-time structural health monitoring left crews and operators blind to progressive fatigue. Proposals for mandatory hull stress sensors and automated crack detection systems gained traction, aiming to give early warning before a minor breach escalates. Classification. Societies started updating their guidelines, calling for closer scrutiny of aging vessels and more frequent checks on high-stress areas between cargo holds. International discussions focused on closing oversight gaps, especially for ships registered under flags of convenience. These steps reflect a growing recognition that regulatory compliance alone cannot guarantee safety. Continuous monitoring and adaptive rules are now seen as essential to preventing another quiet structural failure at sea. Today, over 5,000 bulk carriers cross the world's oceans, many aging and all vulnerable to unseen stress. As global trade accelerates, silent failures remain a constant risk. Engineering margins are thin, and safe at anchor is never guaranteed. The next fracture could be anywhere, at any time.